The functions f and g are defined by calculate inverse of f at 3 multiplied by the inverse of g at 3. It's just such notation. It's just function is e to the power of x and g is x plus 2. And we need the inverse of f at point 3, and actually it's not necessary to find the expression for inverse firstly, because we can rewrite this question in terms of function f. So if we consider the inverse, it means that x for inverse is 3 and y is required, but in terms of usual function, y is 3 and x is unknown. So we can consider y of function is 3 for f and solve for x. And we get 3 is e to the power of x, apply ln, and it becomes ln 3 is ln of e to the power of x, which is x ln e. Ln is 1, it's a property of ln, so x is ln 3. And let's consider the inverse of g at point 3, and also we can consider that y is 3 for g, and it becomes 3 is x plus 2, and we can see that x is 1. So inverse of f at 3 it's ln 3, and inverse of g at 3 it's 1. Hence this product is just ln 3. The next shows that a composite function f of g and inverse of it at point 3 is equal to this. So we need to consider to find a composite function. Firstly, it looks like f of g of x, and we need substitute g of x, x plus 2 for x into f. So it becomes e to the power of x plus 2. And again, we can actually find the inverse and substitute 3 for x, but we can also rewrite this question in terms of function, not inverse. So if we need inverse at 3, so it becomes this function y for usual function is 3, and we need x. So, and again apply ln on both sides, and it becomes ln 3 is ln of e, and it becomes x plus 2 ln e, which is 1. And hence x is ln 3 minus 2. Properties of ln are given in the data booklet, and I have used the next property that ln of x to the power of m, or it may be for any logarithm of to any base, m ln x, and log AA is 1 by definition. So we get the required result. So hence f of g inverse at 3 is ln 3 minus 2 as required. And that's all for this question.